In this tutorial, we will be discussing oxidation-reduction reactions, also known as redox. In fact, most likely you'll be hearing them called redox rather than oxidation reduction, just because it's easier to say. Okay, reactions that involve transfer of electrons are called oxidation-reduction reactions. Redox reactions are responsible for the reason why things rust. You can bleach your hair, the electricity in batteries. So redox happens quite often. In fact, several of the reactions we've seen so far may have actually encompassed redox in the process, and we just haven't really discussed it. Many redox reactions involve reactions with the substance of oxygen. So, when we're looking at oxidation reduction, the fundamental definition of oxidation is the loss of electrons, while the reduction is the gain of electrons. I remember it by Leo Gurr. Lose electrons oxidized. Gain electrons reduced. Leo Gurr. And we'll come back to this as we start doing practice problems. Notice that oxidation reduction must occur at the exact same time. If the electrons are being lost, they have to be gained somewhere. If electrons are being gained, they had to come from somewhere. If one substance loses electrons being oxidized, another substance must have to be reduced. Right now we're just going to focus on identifying the reactions and which is occurring. A reaction can be classified as a redox reaction if it meets one of these requirements. It reacts with elemental oxygen, a metal reacts with a nonmetal, or more generally, the electrons transfer from one to the other. So to determine if the electrons have transferred, the easiest way to go about doing this is to look at the charge of each individual element. Keep that in mind. You have to figure out the charge of every element in the chemical reactions to determine which is being oxidized and which is being reduced, because you have to be able to compare them. So first thing we're going to learn is how to determine the charge. If it's a free element all by itself, like Cu, Mg, something like that that's right off the periodic table, it is 0. Don't be fooled that O2, the diatomic molecules, if they're by themselves, O2, H2, those are also zeros. The oxidation of a monatomic ion equals the charge of the ion. So if it's already been changed, if it's already lost an electron, it's going to be that charge. For instance, sodium, if it reacted with chlorine, is already going to be Na+. The usual oxidation number of hydrogen is a +1, and oxidation number of oxygen is usually a -2. Oxygen comes up quite often, so you want to make sure that you realize the -2. Group 1 is a +1. Group 2 is a +2. Group 7 is a -1. The sum of the oxidation numbers of all the atoms in a neutral compound have to equal 0. The sum of the oxidation numbers in a polyatomic ion is equal to the charge of that ion. These rules are in order of decreasing significance. So that means the most important ones are up here at the top. And then those can cancel out the ones on the bottom if there's a question regarding that. Alright, so HCl. We'll just go through a couple of these practices. H is usually a +1. So that means this is going to be a +1. Cl, since it has to be neutral, it has to equal 0. +1 plus Cl is going to equal 0. So that means Cl must then equal -1. Na2O. Oxygen is a -2. So Na, 2 Nas plus a -2 for oxygen yields once again 0. So that means 2 Nas have to equal a +2, which gives Na a +1 charge. ClO-. Now this is where I was saying that one can outweigh the other. they get less significant as you go down. So the very first one, oxygen, is here, is above rule number 7. So that means oxygen wins. So we gotta put Cl plus, there's 1 negative 2 for oxygen, overall charge of -1. So that means we add 2 to both sides. This is odd for chlorine that you've seen before. You haven't really seen chlorine as a +1, but here it is. KMnO4. MnO4 is a polyatomic ion. K is a monatomic ion. So that's going to be a +1. That follows this rule here as well. So M, N, and 4 oxygens, which have all a -2 charge, all combine to have a -1 charge. That means Mn has to equal a +7 charge, because 4 times -2 is -8. We add 8 to both sides, and that comes out to be +7. SO4 2-, S plus 4 oxygens, which are -2, is equal to -2. So that means S is equal to -8. Pardon. S minus 8 is equal to -2. That means S here is a +6. You might notice that when we're looking at the periodic table, sulfur is usually a -2. But here it's a +6, so you can't always rely on the periodic table when you're determining the oxidation number. Oxidation number and ionic number, when you do the crisscross, are not the same thing. Alright, so now let's see if we can figure out which one is being oxidized and which one is being reduced. So that means we have to use those rules again. So I2O5. We have 2 iodines, and we have 5 oxygens. If we look up here at our rules, oxygen's a -2. So 5 times -2, it's a neutral molecule, so it's going to equal 0. So 2 iodine minus 10 is equal to 0. Rearrange that, and we find out that I is a +5, and oxygen is a -2. For CNO, oxygens are -2 because of that rule, which to balance that out, carbon must be a +2. Iodine is I2. It's a free element, so that means it's 0. And then we have CO2. So we have carbon plus 2 -2 charges for oxygen is neutral. So that means carbon must be a +4, while oxygen's a -2. Now, let's pair up which ones are being oxidized and which ones being reduced. We're looking at the things where the charges have changed. For instance, iodine is here and here. It goes from a +5 to a 0. Our other thing that changed was the carbon. It went from a +2 to a +4. What I usually do here is I look at a number line. Here's my number line. Here's 0. I'm starting with a +5. 1, 2, 3, 4, 5. I'm starting here. Iodine went from a +5 to a 0 and went this way on the number line. Electrons are negatively charged. Because of that, when you gain electrons, you're gaining negative charges. So it's becoming more negative. As a result, it's going to move to the left on the number line, because it's becoming more negative. So therefore, gain electrons reduction, LEOGR. Gain electrons reduction. So this is reduced. Now let's look at that carbon. Carbon started off at a +2 and went to a +4. and went to the right on the number line. It lost electrons. If you lose electrons, you become more positive, which means that you're going to move right on the number line. So, lose electrons, oxidized. So that means that the iodine was reduced and the carbon was oxidized. Alright, let's go through all of that again. First thing you have to do when you start these is look at what the charges are of the individual atoms. So sulfur and 2 oxygens, oxygens at -2, is equal to 0. So sulfur minus 4 is equal to 0. So that means sulfur must be a positive 4. H and O, and oxygen is going to be a -2 again. H and O3. H is going to be a +1. And O3 is an polyatomic anion. So we have nitrogen, and we have 3 oxygens, which are -2s. And that's going to equal all a -1 charge, which puts nitrogen at a +5 charge, oxidation number, and oxygen a -2. Hydrogen's a +1, oxygen's a -2. That was in the rules right here. Hydrogen's a +1 again. This time SO4. So we have 1 sulfur and 4 -2 charges is equal to -2. So that means sulfur minus 8 is equal to -2. That gives sulfur a +6 charge and oxygen a -2 charge. And then NO, oxygen's -2. To balance that out, nitrogen must be a +2. There's a lot of elements here. There's a lot of atoms. So let's try to find the ones that match up. So sulfur is going from a +4 to a +6. Oxygens don't change. They're always a -2 unless it's all by itself. Nitrogen is going from a +5 to a +2. So we found the 2 that changed. So here's our number line. 1, 2, 3, 4 for sulfur, and it's changing over to a +6. It's going to the right on the number line. It's becoming more positive, meaning it's losing electrons. If it's losing electrons, it's being oxidized, Leo. So that means that's being oxidized. Let's look at the nitrogen. We're starting off at 5, and we're moving to a +2. We're moving to the left. We're becoming more negative, meaning that we've gained electrons now. Gain electrons reduced. So that means the nitrogen is being reduced in this scenario. It takes practice, but if you keep practicing, you'll get it. Just take your time and look at each of the individual oxidation numbers.